So we're happy today to have Stephanie LaMassa with us. So Stephanie holds a PhD from the Johns Hopkins University, and she's now on the staff at the Space Telescope Science Institute. So her research interests are in supermassive black holes, galaxy formation and evolution, AGNs, quasars, and all that. So now she's going to tell us today about insights into the feeding habits of supermassive black holes from changing look AGNs. Please go ahead.
All right, thank you. Let me go ahead and share my screen. All right, let's see. I'm not sure if I'm sharing the right screen. Are you seeing the presenter view, or are you seeing the main screen?
We're seeing the right screen, the right one.
Okay.
Yeah.
All right, so I will go ahead and get started. Well, let me see it. Make sure this works. Okay. All right, so are you all able to see the first slide? Just double checking. All right, excellent. All right. So we know that supermassive black holes that are millions to billions of times the mass of our sun live in the centers of galaxies. And when they are in the phase where they are growing by accreting nearby matter, they're observed as active galactic nuclei, or AGN. So this activity leaves imprints on its surroundings that could be observed across the electromagnetic spectrum. And using these signatures, we could understand how supermassive black holes grow and evolve across the universe and learn about their evolution. The central engine of the AGN is an accretion disk that feeds the black hole. So here material spirals through the accretion disk down to the black hole. And in this process, it releases some energy due to thermal radiation. And that gives off light at optical and ultraviolet wavelengths. A corona of hot gas around the black hole inverse Compton scatters those accretion disk photons up to X-ray energies. At somewhat larger scales, but still very close to the black hole, about 1/10 to 1 parsec, is gas that doesn't necessarily accrete onto the black hole, but it orbits around the black hole. And because this gas is orbiting pretty rapidly, if we take a spectrum of this gas, we see that the emission lines are Doppler broadened. So we call this region the broadline region. Gas that's hundreds of parsecs above and below the accretion disk is now in the host galaxy of the AGN. However, because the AGN is so powerful, it can still ionize this gas, and we can see the signatures of that activity. And because this gas is orbiting less rapidly, any emission lines that we do observe in the optical or the infrared spectra are narrow rather than broad. So we call this region the narrow line region. And along the plane of the accretion disk and the broadline region is some obscuring dust and gas. So it has a bit of a toroidal geometry in that the polar axis is clear, but around the accretion disk and the broadline region is where this gas and dust reside. This is still pretty close to the black hole. We're really talking about the center of the galaxy. This obscuring medium is maybe on the scale of 1 to maybe tens of parsecs. But what this medium does is that it absorbs the light that comes out from the accretion disk, the optical and the UV light, and re-emits that light at mid-infrared energies. So as you can imagine, how we view this system will determine what we observe. So if we have a view directly to the central engine, we will see emission from the accretion disk, broadline region, narrowline region, from the obscuring medium. And so if we take an optical spectrum, we see a power loss slope to the continuum. That's blue, so that means there's more energy at the smaller wavelengths compared to the longer wavelengths. And that's from the accretion disk. We also see these broad emission lines from the gas that's orbiting rapidly, with those narrow emission lines superimposed on top of them. If, however, our line of sight is through that obscuring medium, that effectively blocks the accretion disk and the broadline region from view. So if we take a spectrum, here this is an optical spectrum from Sloan, we basically tamp down that blue power law continuum and we get rid of the broad lines because they're blocked. So we only see these very strong narrow emission lines. And historically, AGN have been defined by their optical spectra, where the type 1 AGN show these prominent broad emission lines in the ultraviolet and the optical, and the type 2 AGN are defined by their lack of broad lines, having narrow lines only. And the theory of AGN unification says, at its most basic level, that this dichotomy between type 1 and type 2 is solely due to the viewing angle of the observer, whether or not we have a direct view to the central engine or we're viewing the AGN through that obscuring medium. So now we could have a little bit of a pop quiz where we could classify this AGN spectrum based on what we know. So in the spectrum, we do see broad emission at H alpha and also at H beta, though it's a little bit weaker. So we would call this source a type 1 AGN. And in the bottom spectrum, we don't see prominent broad lines. The broad component around H beta isn't there. So if you have a trained eye and you look around H alpha, you might be able to see that there's a little bit of a broad wing. So it's a type 1.9. I didn't really talk about intermediate types in the previous slides. But still, if we were to interpret these spectra through the lens of AGN unification, we would say that the top spectrum is from an AGN where we have a direct view to the central engine, and the bottom spectrum is an AGN where our line of sight to the accretion disk and the broadline region is obscured by dust. However, both spectra are from the same source, just observed at different times. The top spectrum comes from the Sloan Digital Sky Survey. It's an observation that took place in 2000. And the bottom spectrum is from the BOSS survey within the Sloan Digital Sky Survey from 10 years later. So the source is what's known as a changing look AGN, in that its optical spectrum changed dramatically between spectroscopic epochs. If you look kind of at the blue end of the continuum, you can see it somewhat goes down between the two observations, but even more strikingly is seeing how the broad H alpha became much weaker and the broad H beta disappeared. So this isn't the first changing look AGN that had ever been discovered. Perhaps the first instance was discovered in the 1970s with NGC 7603. And you can see that between observations, the broad H beta line weakened substantially and then started to reappear. And this is what we sometimes see in these changing look AGN is that the Balmer lines, which are transitions of hydrogen, become weaker in some cases. They could disappear between spectral epochs. They could appear between spectroscopic observations, or they can strengthen and then weaken. And often this is associated with a change in the continuum, either becoming bluer or redder, or stronger or weaker. And there have been several hypotheses to explain what could be driving changing look AGN. And the top two have to do with the AGN itself. Perhaps that obscuration is variable. In the cartoon that I showed, I depicted it as a a distribution of clouds, because there is some evidence that this obscuring medium does have a clumpy distribution. So you can imagine if you have clouds that are circling around the broadline region, perhaps you could have these eclipsing clouds that either cover the broadline region or unmask it as those clouds transit. It could be instead that the accretion onto the black hole is changing. So the amount of ionizing continuum that's available varies between observations. And the analogy that I like to use here is that of like a dimmer switch. That if you turn down the dimmer switch of a light, then you have less energy to ionize the surrounding gas, which could be manifested by having weaker broadlines. Or there could be external factors. Maybe this has nothing to do with the AGN at all. Maybe it's microlensing, where there's a foreground star that, that transits between the observer and the galaxy, and that causes the AGN to appear to brighten and then fade. Or maybe these could be imposters. Maybe these could be other transient phenomena that just happen to briefly masquerade as an AGN. For example, maybe we could have a supernova in the center of a galaxy that temporarily has some broad bomber lines that we might ascribe to an AGN. Or maybe we could have a tidal disruption event. So these are objects where a star that gets too close to a black hole can be tidally shredded, and that material that's shredded off the star can circularize into a debris disk, fall onto the black hole, and light it up. Oftentimes, these tidal disruption events, or TDEs, are discovered in galaxies that have otherwise dormant black holes, because it's kind of hard to tell the difference whether or not a transient event in an AGN is due to something related to the AGN, to the accretion disk, or if it's due to a star that's being tidally disrupted. And actually, the connection between TDEs and variable AGN is really interesting. But what I'm going to focus on in this talk is whether we could distinguish between intrinsic changes in the AGN as drivers of what could be causing the variability. And in particular, we'll start out looking at whether or not variable absorption can be an explanation. And there is some precedence for this based on some interesting results on X-ray changing look AGN. And here I make the distinction of X-ray changing look because a handful of sources were discovered to have had their X-ray spectra vary dramatically on the time scale of days. And this is an example of one of those objects, NGC 1365, where between the first, in a monitoring campaign of this object, between the first observation and the second observation, the X-ray spectrum changed dramatically, weakened dramatically between 4 to 6 or 7 keV. And then in third observation, the spectrum returned to its original state. When Risoliti and collaborators modeled the X-ray spectra of this source, they found that this dip in the X-ray light was best described by heavy amounts of obscuration. That the gas that has a very high column density, that's at the Compton thick levels. And what they found is the way that they describe it is that it could be due to an occulting cloud that transits into the line of sight, blocks the X-ray continuum, and then continues on its orbit. And based on the timescales of the observations, they say that this cloud would probably be within the broadline region itself. So it's reasonable to ask if something similar is at play with these changing look AGN, where the optical spectra vary dramatically. One thing to note, though, one important caveat, in that all these classes of X-ray changing look AGN, where the X-ray spectra change a lot, and it's likely due to eclipsing clouds, the optical spectra never changes. It always stays in its original state. But still, it's worth seeing whether or not this variable absorption hypothesis could explain these types of sources. So some work has been done to test this explicitly by fitting extinction to the optical spectra of changing look AGN. For J0159, we tested this by taking the top spectrum when the source was in its bright type 1 state. And we fit that spectrum and we froze all the model parameters to the best fit model. And then we just added a screen of extinction. And we said, if we just allow that extinction to vary, can we replicate the spectrum when it was in its type 1.9 or dim state? And this was the result of that exercise. In general, we get a good fit to the overall spectrum, except around H alpha, where there is a broad wing to the H alpha line that's not well fit, especially when we allow there to be a broad component to the line in our model. Other groups have done similar analyses with the changing look AGN that they've discovered. In particular, Chelsea McLeod and collaborators did this for a sample of changing look AGN that they looked at a year or so later. And here's an example of just one of those objects. So the red spectrum is a spectrum of a source in 2002, where we see these very prominent broad emission lines, as well as a very blue continuum. The second spectrum in black is a spectrum of the same source in 2014, where we see that that blue continuum is completely attenuated away. And the broad emission lines, especially H beta and H gamma, become much weaker. And what McLeod and collaborators did was to take the spectrum from 2002 and apply different extinction laws from the Small Magellanic Cloud and the Milky Way, shown by the blue and the gray lines in this plot, and see whether or not they could recover the spectrum from 2014. And we could see that it doesn't work. It doesn't match the continuum, and even more strikingly, we could see that there's a residual broad H beta line and residual broad H gamma line in this toy model that is not represented in the data. We could also look at the line profiles themselves in the spectra to get a sense of the gas kinematics. And what's been observed in some of these changing like AGN is that in the state where the AGN fades, there's still a broad component to H alpha that's visible. But in that dim state, the H alpha line is broader than it is than when it's in the faint state. Renault and collaborators showed this for one of the objects that they discovered. John Runn and collaborators demonstrated this for a couple of the objects that they studied. And we also found something similar for J0159. So one thing that's interesting about the full width half max of the H alpha line being broader is that this indicates that this line is coming from gas that's closer to the black hole. So it's orbiting faster, causing the line to be more Doppler broadened. And we also used the results of this to measure the black hole mass of this particular AGN using the full width half max of the H alpha line and the continuum luminosity of the AGN at 5100 angstroms. And what we found is that when we do this with the measured parameters from the spectrum, when the source is in its bright state and in its dim state, we found very consistent black hole masses. so that the full width half max of the line broadened in lockstep with how much the continuum faded. And this gave us further evidence that even in the dim state, we have a direct view to the central engine, to the broadline region, such that we're able to map out the motions of the gas under the influence of the black hole. From the optical photometry, we could also get a sense of the timescale of when these transitions happen. The spectroscopic observations, so we're very fortunate to have them because especially in these early cases, the spectroscopic observations are completely serendipitous, but they are separated by about 10 years or so on that time scale. For the photometric measurements, we sometimes have higher cadence of observations. So we could get a better sense of what the time scale is of when the source might brighten or dim. So one time scale that we could estimate is the amount of time that would take for a cloud to eclipse the broadline region given by this formula. And then we could compare that with the time scale in which we see the change in the brightness from the AGN. So for J0159, we're pretty fortunate because the source was observed in the Stripe 82 region of Sloan. So this was a region of the Sloan Digital Sky Survey that had multiple epochs of photometric observations because this area of the sky was monitored as part of a supernova survey. So because of that, we have pretty high cadence of photometric data points to get a sense of when the source started to decrease in brightness. So what's shown here is the brightness of the source in the 5 different Sloan filters as a function of time. And so we could see the source dimming between the Sloan spectrum in 2000 and then the later spectrum, and we could estimate what the time scale is of when the source dimmed. And the time scale of that change is about 3 years. While if you calculated the crossing time from the previous slide, that crossing time for a cloud to eclipse a broadline region would be 10 to 20 years. And other groups have done similar calculations comparing the photometric timescale for changes of the objects that they discovered compared with that crossing time. And again, crossing time is much longer than the observed change. So it seems unlikely that eclipsing clouds could be responsible for driving this change. We could also use information from mid-infrared photometry as an extra clue as to what could be going on. So the mid-infrared emission in AGN, again, is going to come from that obscuring medium that's further away from the black hole. So this is that obscuration that is beyond the accretion disk and the broadline region. So some groups have used the availability of data from the WISE observatory, which has multiple observations over time at mid-infrared wavelengths to try to get a sense of what the mid-infrared light curves for these changing look AGN look like. So this is some work done by Sheng et al. A couple of years ago, where here I'm showing the optical light curve where the vertical lines indicate when the source was in a bright state, a type 1, and spectroscopically when it was observed to be in the dimmer state where most of the broad bomber lines disappeared when it was at a type 1.9. And from the optical light curve, you could get a sense of when the time scale is for when the source faded. And the bottom panel shows what the mid-infrared light curve looks like. So again, what we're seeing here is that the mid-infrared light curve goes from bright to dim, somewhat lagging a little bit of the time scale of what's happening in optical, which makes sense because the dust is further out. Again, they were able to invoke the timescale argument to say that the crossing time for something to obscure the broadline region or even the obscuring medium is much greater than the timescale of the change that they observed. But also, the mid-infrared emission is not significantly affected by dust extinction. So if you want to ascribe the dimming of the mid-infrared light by dust, you would have to have a very high amount of extinction. And so you could calculate what that would be. But then if you extrapolated what that would do to the optical light, then the optical light should be much, much more attenuated than was observed to be. And that wasn't what was observed. So again, another indication that perhaps it's not variable obscuration driving the change. And Yang et al. Looked at the colors of the changing look AGN that they studied. One thing that they found when they looked at the optical colors is that when these changing look AGN were brighter, they were bluer. And this is interesting because normal AGN show this phenomenon that so normal AGN do vary, perhaps certainly not as drastically as these changing look AGN, but when they are brighter, they tend to have bluer colors, perhaps related to temperature fluctuations in the accretion disk. So this is something that you would expect from objects where you do have a direct view of the accretion disk and the broadline region. When they looked at the mid-infrared light curve, they found that the AGN were redder when brighter instead of bluer. And what they ascribe this to is that when the AGN is brighter, then the obscuring dust is heated up more, which causes the colors to be redder. So much of the observational evidence disfavors variable extinction as an explanation for many of these changing look AGN, including a couple of points I didn't have time to touch upon. The X-ray spectroscopy, radio variability, polarimetry measurements are all consistent with the AGN itself intrinsically changing and it not being due to occulting clouds transiting into or out of the line of sight. And some very nearby changing look AGN have been the target of monitoring campaigns, and they show this dimming and rebrightening behavior, which is pretty interesting, and again speaks to perhaps having a direct view of the central engine and just seeing something intrinsically changing in these objects. So perhaps a better formulation is to think of these objects as changing state AGN rather than changing look AGN. And Matt Graham makes this point in his recent paper about that, where changing look AGN is really kind of this observational catch-all description for these objects, where there's not even necessarily a consistent definition in the literature. While changing state AGN speaks to the fact that there's something physically changing in these objects. So it's more of a physical descriptor of what we're observing. So this brings us to the question of what's causing this state change. And presumably it's related to accretion onto the black hole. So one of the typical timescales that's thought about in accretion physics onto a supermassive black hole is the viscous inflow timescale from the standard Shakura-Tsuniaev thin accretion disk model. So it's the amount of time that it takes for material to spiral outwards through the disk into the center. And when this is calculated for many of these changing state AGN that have been discovered, the inflow timescale seems to be too long. So it's thought that perhaps this is not the process that might be most relevant for driving the state change in these objects. So lots of focus has instead related to processes that might look at or might work on scales of the inner accretion disk. And so some relevant timescales here are the orbital or dynamical timescale, which is related to 1 over the Keplerian orbital velocity of a parcel of gas at a certain radius from the black hole. And if we're talking about stuff that happens kind of close to the inner accretion disk, this time scale is a little bit too short. It's on the order of weeks or maybe months. But the thermal time scale, which is the time scale at which the accretion disk heats or cools, is related to the orbital time scale modified by alpha, which is the viscosity parameter in the standard Shakura-Sinayev accretion disk model, which speaks to the efficiency of angular momentum transport through the disk. That thermal time scale could be relevant for these objects. A couple of groups have shown that the thermal time scale for the specific changing state AGN that they've studied is commensurate with the time scale of variability that they observed. So that could be a promising avenue. It's also possible that the change of state could be related to heating or cooling fronts propagating through the accretion disk. Where here the time scale would be the thermal time scale modified by the local sound speed in the accretion disk. And for this to be viable, a modification to the standard Shakura-Sinayev thin disk would be needed. So for this model, there is some material between the innermost stable circular orbit of the black hole and the inner edge of the accretion disk, such that the inner edge of the accretion disk puffs up due to a torque. And Nick Frost have this nice cartoon in their paper from 2018, where they invoke this explanation to describe a changing state AGN that they discovered that's showing this fading and rebrightening on a time scale of about 20 years. So this top panel is showing this the initial state where there's that inflated thin accretion disk due to a non-zero torque between the black hole and the inner edge of the accretion disk. Then they say some triggering event happens, and they're kind of agnostic as to what that event could be. But they say maybe it's a change in the accretion rate, maybe it has something to do with change in the viscosity, but it's something that causes that torque to go near zero and causes the accretion disk to flatten, cooling the disk. And this propagates a cooling front inward, starting out inwards towards the disk, going radially outwards. And observationally, this will cause the AGN to appear to fade. Then at some point, the cooling front stalls and a heating front propagates radially inward to the disk, which would be associated with the AGN rebrightening and the inner disk puffing up again. And they predict that if this model is correct, that the accretion disk should return to its initial state right about 2019, 2020. So I haven't seen anything since then. I don't know if they've taken any follow-up spectra to show that the spectrum has indeed returned to its initial state from 2000. But they do point out that the timescales for this cooling front and heating front propagation does match the timescales of the observed changes that they see in this changing state AGN. Another possibility is that there could be a spectral state transition similar to what's observed in stellar mass black holes. So these are black holes that are 5 to 15 times mass of our sun. and they're in binary systems. So they are accreting matter from their donor stars. And these stellar mass black hole binaries have been shown to be extremely variable on days timescales. And this variability is associated with changes in the spectral state of the black hole binary. So perhaps something similar is going on in supermassive black holes, that we could use their smaller mass cousins as analogs. And the key factor, or the key parameter for these objects, is the Eddington ratio, which basically scales as the accretion rate, how much matter is falling onto the black hole. And so in the X-ray binaries, there's a critical transition at 2%, the Eddington ratio, at which a spectral state transition happens. And it's thought that at the spectral state transition is where the inner edge of the accretion disk truncates, and it's instead replaced by an accretion flow onto the black hole. So John Runn and collaborators looked at this for a sample of changing state AGN, where they parameterized the spectral slope to be the spectral state to be the spectral slope between the ultraviolet and the X-ray energies. So connecting the emission from the accretion disk, the inner edge of the accretion disk that's releasing UV light, with the X-ray corona as a way to probe the geometry. And they associated that with the Eddington ratios of these changing state AGN. So this is a cartoon from their paper where they show in the high soft state, the AGN is accreting pretty efficiently at about 10% Eddington. And it's associated with what's called a soft alpha OX, which means that lots of bright UV emission from the accretion disk is being observed. As the Eddington ratio drops closer to that critical value of 2%, then the spectral index hardens. The observed UV emission becomes much fainter. And one possible way to explain this is perhaps this is where the inner accretion disk gets truncated, and so there's less UV emission to be observed. And they say if you keep on going below that threshold of 0.02 Eddington, then the spectral slope tends to soften again because you have emergent UV emission. And they say this could be from that accretion flow onto the black hole. It could be from a jet. And that this could be that the similarity of what they're viewing in the changing state AGN with what's observed with black hole binaries could be a good descriptor of what could be triggering these changes in the AGN. Noda and Dunn looked at this for a particular changing state AGN, and they really hammer home the point that, once you get to cross that critical value of 0.02 Eddington, then the shape of the ionizing continuum changes, providing fewer photons to ionize the broadline region. So now that we're getting to the era where we have samples of changing look AGN from, moving from serendipitous detections to larger samples where we could get a sense of their properties statistically, we could ask whether or not they have specific traits that could give us some answers or some clues as to what might be going on. And in particular, in McLeod et al. And in Graham et al. 2020, they showed that the changing state quasars that they've studied do have low Eddington ratios. So that observation can be consistent with this state transition that we see in stellar mass black holes. McLeod et al. Also point out that there is a model that a wind from the accretion disk supports the broadline region, but that at certain Eddington ratios, that accretion disk wind fails, and that will result in the broadline region no longer being illuminated. So it could be that the Eddington ratio or the accretion rate onto the black hole might be the critical parameter that describes what it is that we see, and could be what's responsible for the physical mechanism of what's triggering the changes in these AGN. So the study of changing state AGN is a burgeoning field. From 2014 to 2016, there were there was a handful of papers that just had these one-off discoveries of serendipitous detections due to there being either archival observations of repeat spectra of specific sources or follow-up spectra of objects for other reasons than finding these dramatic changes. And since then, groups have then done more systematic work to identify promising changing look AGN candidates based on looking at features in the light curves to try to find things that are highly variable and follow them up with surveys to identify more of these objects. So we've really moved from the era of one-off serendipitous detections to systematic searches to understand the population more statistically. And in the current era that we're in now, this field is just going to continue to grow. The Zwicky Transient Factory, which is ongoing, the Rubin Survey Telescope, which will be online in a couple of years. These are great photometric surveys that give us the opportunity to be able to identify transients and find which ones might be the most promising to follow up with spectroscopy to observe the features of these objects to really understand the gas kinematics and probe accretion onto the black hole. In tandem, we do have ongoing spectroscopic surveys like Sloan. In particular, the black hole mapper part of the Sloan Digital Sky 5 survey will be doing repeat spectroscopy of known quasars or known high luminosity AGN. And the goal is just to get a sense of AGN variability at a range of different timescales. But part of that means that we are going to be discovering more of these changing state AGN just as part of that process. And it seems pretty clear that many of these objects are really telling us about the accretion onto the supermassive black hole rather than an external factor. And it seems likely that it's related to processes that operate on the scales of the inner accretion disk, including the hypotheses that I discussed in this talk, as well as a couple of other possible models that I haven't had time to go into. I just kind of leave them here for reference. Some of the challenges going forward is really, especially when we think about these photometric surveys, is there's lots of transients. We're kind of like in the golden era of transient astronomy. So being able to distinguish what transient is due to changes in intrinsic changes in an AGN or pre-existing accretion disk around a black hole, and which are external imposters, is a challenge. Though I think the link between TDEs and highly variable AGN is an exciting one. So I think there's more opportunities there than challenges. But it's, disentangling what the causes are is not always clear. Also, having contemporaneous multi-wavelength data to test theoretical models is really important. And sometimes we just miss the opportunity, especially for lots of these objects that have been discovered through archival databases. These discoveries are made years after the observation. It's too late to get that supporting multi-wavelength data to really understand what's going on. But if we're able to be more cognizant of that going forward, we could better link the observables to the physical models to try to understand what it is that's causing the state change. But now that like we've entered this regime where these objects are no longer mere curiosities, but samples of objects that are teaching us statistically what might be happening in these supermassive black holes, this gives us an excellent probe of accretion physics and EGN lifetimes. And I'll just leave it there. Thank you for your time.
Thank you. Thanks, Steph.
Thanks.
Yeah, people are clapping. So we have time for some questions. There was one question that Magdalena sent to the chat. This was around the time when you were discussing the basic regions around an AGN, broad, narrow, obscure, etc.
Mm-hmm.
She says, do you have a number estimate for the maximum radius typical for AGN disks?
Yeah, typical for AGN, that is a good one. I don't know what the maximum is. So I'm trying to get back to that slide. I mean, I kind of just leave it to be, very, very, very tiny. Yeah, I don't know off the top of my head, but usually the size scales we think of are, thousandths to hundredths of a parsec.
Okay, Angelo.
Hi, Steph. Thanks for a great talk.
Thank you.
So last week, I was at a conference for the next generation Event Horizon Telescope, and we were trying to brainstorm new things that we could do. And one idea that came up was to use the next generation EHT to try and catch a changing look AGN mid-transition. Yeah, so I'm wondering about your thoughts on how one would actually do this. Like how long, if you had a source, how long does it take for it to change states, and how long would you have to wait for you to get lucky and for it to start doing that?
Yeah. Oh, that gives so many exciting possibilities. So I mean, I think that the biggest challenge might just be, I mean, like better than me what the resolution is of the Event Horizon Telescope, and like how, I mean, I would assume it'd have to be a very nearby AGN for this to be plausible.
We could still potentially learn stuff from resolving the jets.
Okay. Yeah. So I would say that, so I think that like the photometric studies are really going to be key here, especially something like Rubin that's going to get like, the cadence of some of these objects will be like on days time scale. So I think if you were able to, if you knew where the existing AGN are, and you were able to get light curves quickly, and you saw something fade over the time scale of like a couple of days, you got a follow-up spectrum and you saw broad lines disappear, then I think that's something that you could then follow up. But again, for Event Horizon, I know that coordinating everything for observations, right. Like it's like that's like a year time scale. So I mean, like some of these things stay like in their states for a while. So I guess the question is whether you want to observe these things when they're bright or when they're dim. But for many of these, they do seem to kind of stay in a bright state or a dim state on the order of years, maybe. So I think you could probably identify them and then plan to observe them. So I think there's some promise there. That's pretty cool.
Thanks.
Yeah. Any other questions? I'm curious about something myself, actually. So with regards to parameter estimation, so you showed at some point that you get a consistent estimate for the mass from using hydrogen lines. People use the iron lines for spin estimation. Would the specifically the broadening of those lines is what determines the spin measurements. How much are those affected by changing looks?
Yeah, so that's a really good question. So I don't think I have this slide in this paper, so, or in this presentation. So the iron K alpha line in the X-ray spectrum, there's so many fun things you could do with that line. So one of the things that I found, so actually let me just get to this slide so I can at least point to it. This paper, the Husman plus 2016 and LaMassa 2017, looked at the X-ray spectra of Markarian 1018. And there was a prominent iron K alpha line in that object. So one of the things that's interesting about iron K alpha is that some people use that line to try to probe the spin of the black hole, with the idea that the X-ray photons can impinge on the accretion disk and then get reflected off the accretion disk into the line of sight. And if it's moving and with like rapid motion, the line could become Doppler broadened. So that gives you a way to measure black hole spin. Another way that you could get broad emission lines is that the X-ray light can reflect off of the obscuring gas and then get reflected into your line of sight. So when it gets reflected off the gas, it releases iron K alpha photons. And so you could get that feature in reflected light. And if you have lots of heavy obscuration, that can tamp your continuum down to low levels. So if you measure the equivalent width of the iron K alpha line in an obscured HEN, lots of times you'll find that equivalent width is large, just because it's measured against a depressed continuum. So for Markarian 1018, there was an X-ray spectrum when the source was bright and an X-ray spectrum when the source was dim. And in the dim state spectrum, the object, the iron K alpha line looked more prominent. And so one of the questions that I had when I saw that was, well, is this due to obscuration, or is it just due to the continuum dropping and the line not having a chance to respond to the change because the line is formed in material that's further out. So what I did was to take the X-ray spectrum and fit it with these self-consistent models where the transmitted component that gets attenuated is linked to the reflected component, which is linked to the iron K alpha line, to get a sense of what was going on. Because originally, when I saw the large iron K alpha line, I'm like, this means it's obscured. Like this is why it's happening. But based on the modeling, we came to the opposite conclusion that no, what happened was the continuum dropped and the line didn't respond to it. So we were able to use the line as a probe as to what was going on, but not necessarily as a probe to measuring the black hole spin. Sometimes for some groups, measuring black hole spin via the iron K alpha line could be a little bit controversial because there are a couple of ways that you could get a broad line. It could be due to obscuration, it could be due to Doppler broadening. And so trying to disentangle what those effects might be on the spectrum is not always straightforward. So yeah, I haven't looked at trying to model the spectrum with a component that ascribes it to relativistic reflection, which would cause a broad line. But I could say that it was well described by this other model.
A quick follow-up. So these spin measurements via the K alpha line typically produce high spins. Is it easier to disentangle this? In that regime, could that be a reason, or is it just an accident?
Yeah, so that's a good question. And I think So, you know, there are probably like better experts at the CFA who could speak to this than I can. I could imagine that it could be a case where it might just be easier to see that if the black hole is spinning rapidly, but that is something that is has been noted before, that when looking at black hole spins measured from the K alpha line, they tend to be skewed towards, like, you know, black hole spin of like 0.9 to 0.99999, which you know, maybe it's an observational bias. I don't have much expertise myself doing those measurements.
Okay, yeah. Do we have any other questions? Or going once, going twice? Okay, it's about time. So let's thank Stephanie again for a very nice talk. Thank you very much.
Thank you for having me.
See everybody back next week. Bye-bye.
Bye.